Okay guys, welcome to this video. I'm going to be talking about feature selection methods for content-based image retrieval. And this presentation is derived from my research experience, which resulted in this IEEE Access publication. As you can see, the title is Genetic Algorithm-Based Feature Selection from High-Dimensional Descriptors for Improved Content-Based Image Retrieval. And okay, to start, I think the best starting point is to define image retrieval, or in general, what is information retrieval. Information retrieval is where you have a database of a high number of documents, and you want to give this document a query and expect it to retrieve the similar items from that database that are similar to the query that you give the system. Okay, so as you can see, we have a bunch of documents here, and I'm sorry, the documents are here, and we give it a query and we expect it to fetch a bunch of documents for us. And okay, so if the data, these documents that we are working with are image, we call it image retrieval, which is a subset of information retrieval. Okay, so we have multiple types of image retrieval, which depend solely on the type of the query that we are giving the system. Okay, so here we have the similar schematic diagram as we've seen in the previous slide. The only difference is that the input query is a text. Okay, so here the word elephant has been inputted to the system, and the text-based image retrieval system has fetched these images from the image dataset for us. Okay, so if the input query is a text, we call it text-based image retrieval. And of course, the output is always image because we are retrieving image, right? It's image retrieval. But if the input query is a text, we call it text-based image retrieval, or in short, TBIR. But the focus of this study, and mostly the state of the image retrieval research, is mainly focused on content-based image retrieval. Okay, in these type of image retrieval systems, which we call them CBIR in short, it's similar to the previous ones that we have seen. The only difference is that the input query is actually an image itself. Okay, so you're giving the database, the image retrieval system, an image, a query image, and we are expecting it to retrieve similar images from the database for us. Okay, so as you can see here, we have the image dataset, and here is the query image, which is a red box, and the system successfully retrieved these four images from the dataset for us. So this is called content-based image retrieval. And okay, so you might ask yourself, how the hell does a image retrieval system works? Okay, so the backbone of all of these content-based or even text-based image retrieval systems is a similarity search. Okay, so we have a bunch of images in our image dataset, and we are giving it a query, right? Whether it is either a text or an image, as we discussed previously. The thing that the retrieval system must be able to do very well is to find the similarities between the query image and each and every images in the dataset. Okay, so it is able to retrieve similar images. The algorithm in machine learning that provide us with this service of similarity search is called a k-nearest neighbor, or KNN for short. For example, if you look at this diagram, this red image, which has a red boundary, is the query image. And we see we have a bunch of dog images here, a bunch of panda images here, and a bunch of cat images there. The KNN, or the similarity search algorithm that we use, which is the backbone of the image retrieval systems, must be able to find the most similar image in this whole data set, which of course is the dog images which are closest here, right? As I said in the previous slide, these similarity search algorithms, or most specifically KNN, needs a distance metric for it to find the distance between this query image and all of the other images in the data set. So we have different kind of distance metrics. As you can see, we have Euclidean distance, cosine distance, Hamming distance. Hamming is mostly used for binary feature sets, but it's a distance. We got Manhattan distance, Minkowski, Chebyshev, Jaccard, and more complex distance matrices. Yeah, you might ask yourself, okay, so we have the similarity search algorithm, which is KNN, and we have decided to use, for example, let's say Minkowski distance. Of course, the distance metric must be decided in an ablation study. It's a hyperparameter of what distance metrics to choose. So it's not like a rule or always default choice to use one of these distance matrices. Okay, you have to check which one of them suit your specific dataset better. So imagine we have selected KNN and also, for example, one of these distance matrices like Manhattan, and you might ask yourself, what exactly are we matching here? What exactly are the two things that we are trying to find the similarity? And that takes us to feature extraction methods in content-based image retrieval. Okay, as I said previously, we have a input query image, and on the other hand, we have a bunch of images that are in the dataset, right? We can't directly compare those images of the input and in the dataset directly, right? So first we need to extract a bunch of features from both the input query image and the images in the dataset, and then perform the similarity search algorithm that we have. The state of feature extraction in content-based image retrieval is mainly divided into two sections: the handcrafted methods and, as we will see later, the deep learning methods. Okay, so as for the handcrafted methods, there are various feature extraction methods gathered by the researcher of the content-based image retrieval field to try to extract richer and richer features from the images. We have edge detection methods, shape-based method, texture analysis like a local binary pattern, color and intensity features, transformer-based features. Okay, so transformer-based is one of the deep learning methods which we will see in the next slide, so it's not a handcrafted. We have blob detection, local feature descriptors, and corner detection. But the type of feature extraction methods that are commonly used now are not those handcrafted methods which we saw, but are actually the deep learning methods, to rely on a deep learning model like a convolutional neural network, a CNN, or a more modern ones like vision transformers or vision mambas, or these kind of things, to extract the features for us, which is mainly the last fully connected layer of the model. Okay, so we pass the image into the network and extract the last one or last two layers, fully connected layers, and store them as feature, and then of course perform the similarity search algorithm over them. And okay, for performance metrics, we mainly use precision at k and recall at k, alongside MAP at k. Your If you had any background in machine learning, I believe you are familiar with precision and recall and F1 score. But in image retrieval systems, and generally in information retrieval, we also have an at k at the end of these metrics. Okay, so we have precision at k rather than precision, and recall at k rather than recall. Okay, this is because the information retrieval system is sensitive to k, which is the same k from k and n, and it defines the number of images and number of things that we want to retrieve actually. So if we say the k is 10, it means that basically we are trying to retrieve 10 images according to the input query from the dataset. And this is the formula. Of course, we have more advanced metrics like MAP, which is the mean of another metric called AP at k, which is a combination of precision at k and a relevance, very simple equation here. And as for the datasets that are mainly used in content-based image retrieval research, we have the Corel 10K dataset, which you can see a bunch of samples here. We also, as you can see here in Corel 10K, we have 100 classes, and each of them has 100 images. Okay, so totally we have 10,000 images. This is why it is called Corel 10K, right? The 10K comes from the number of images in the dataset, and it's a fully balanced dataset. We also have a GHIM, which I believe have 20 classes, and each of those classes have 500 images, resulting in, again, 10,000 images. And yeah, these two are the most famous datasets that the research of content-based image retrieval is mostly done over. Okay, so now we get into the research that I did, which is directly related and try to solve the problem of the curse of dimensionality. If you have any background in machine learning, I'm definitely sure that you are familiar with this phenomena, which is referred to as the curse of dimensionality. When we are trying to extract features, we can, of course, we have different and various algorithms to perform the feature extraction methods for us, right? So we had handcrafted, we have deep learning, we might even combine those and get hybrid methods. But we could have many and many features. But as I said in this slide, more features are not always better, okay? So you may say to yourself that we add all of these features, we concatenate them, we extract richer and richer features and increase this number of features that we have. But what happens in practice is that actually a very, very high number of features actually result in worse performance. And this is called the curse of dimensionality, that not always having a higher and higher number of features is beneficial to us. So in order to mitigate this problem of curse of dimensionality, we use something called feature selection. Okay, so imagine these are our features that we extracted, whether using those deep learning methods or I don't know, the handcrafted methods that we saw. And what feature selection system here does is that it only selects a few of the features among these features, but with one condition. Okay, So we want to only select a subset of the features we have here, but we want to get the same performance, of course. Okay, so these three selected features must be able to do relatively good performance compared to all these, high number of features which we have here on the left. So this is all the story of feature selection. And okay, of course, feature selection has its benefits. It removes irrelevant features. It increases the performance of our model. It makes training faster. It's easier to debug, easier to build, and easier to understand, of course, because when you have a more limited number of features, it's easier for you to analyze and build and debug them. So the algorithm that we used here is to perform the feature selection is an algorithm called a genetic algorithm. A genetic algorithm is the type of algorithm which we call optimization algorithm. So they are not necessarily a feature selection algorithm. If you are familiar with machine learning, I'm sure that you have heard of PCA, Principal Component Analysis. PCA is directly a feature selection algorithm, okay? But genetic algorithm and the whole evolutionary algorithms are more optimization algorithms, okay? So we are trying to use an optimization algorithm and try it and the optimization task which we expect it to perform is feature selection for us, okay? And we have decided to use a very, very simple genetic algorithm as the feature selection method here. And I'm not going to get into the details of this genetic algorithm, but what it does is that it has some genes which we define it as whether 0 or 1. A gene of 0 means that that feature is excluded and it's not in the final selected features. And a gene of 1 means that that feature is actually selected and is going to be included in our feature set after the feature selection algorithm works. Then we have a chromosome and we generate a population, and after doing some tasks like crossover and mutation and these kind of things, which you can read in the paper if you're interested and learn there, we try to optimize this fitness function. Okay, so fitness function in the literature of optimization algorithms means the function that you are trying to optimize. Okay, in this case, we are trying to maximize this fitness function, and as you can see, it is composed of two sections. The first one is this upper item, and the second one is this lower item. The upper one is basically trying to say that maximize the precision. Okay, precision at k is the metric that we saw, so we are trying to maximize the precision of the selected feature subset, and at the same time try to minimize the number of selected features to the total number of features. Okay, so what this fitness function is saying is that by maximizing this fitness function, you are both maximizing the precision that you are getting from this act of feature selection, and at the same time reducing the number of features, right? Because this alpha, it's 1 minus alpha and there's a negative here, so the number of features is actually going down, and at the same time the precision at k is going up. So this is the algorithm that we used, and in this table we have the results over a bunch of dataset. Here we see Corel dataset, Corel 10K dataset, and GHIM 10K dataset, which I showed a bunch of samples. And as you can see, the precision has gained over 20% in the Corel 10K dataset, and around 20% again on the GHIM dataset. But the most interesting part for us is the number of features, which we see has been substantially lower. Initially, we had 1,364 features, and it was reduced to only 241 features for the Corel 10K dataset, and for around 3,000 features from the GHIM, it was reduced to only 218, which is a very, very good performance of this fitness function, which we proposed as a novel feature function, fitness function in the literature of content-based image retrieval, and the good job that the genetic algorithm has done to optimize this fitness function for us. So yeah, this was the research that I did on content-based image retrieval and the novelties that me and my supervisors contributed to this field, and the results we gave. I hope that you enjoyed this presentation and have learned something new out of it. So have a good day.